Hello and welcome to the first of our 8-week webinar series called Advancing in Predictive with Alteryx. This is the first webinar, so we will be covering linear regression today. Just as a quick kind of reminder and for you to mark on your calendars, these are the upcoming webinars and their dates that we have for this series. As a reminder, all the webinars will be on Thursdays at 12 p.m. and we are very excited for this upcoming content. And a little bit of some introductions. I'm Rachel Mason. I'm the marketing specialist here at Teknion Data Solutions, and Teknion is very excited to be hosting this webinar. Today's webinar will be led by Dr. J. Kyle Roberts, who is our data scientist here at Teknion Data Solutions. And a little bit about Kyle: he's held a few professorial positions at Southern Methodist University, Baylor College of Medicine, and the University of North Texas. In addition, he co-authored the Y-HAT package in R, and he is an expert in multi-level modeling and co-authored the Handbook of Advanced Multi-Level Analysis. So at this time, I'm going to hand over to Kyle to kind of get us started.
All right, well, we're excited to present to y'all today. So the idea is that we're going to take maybe about a 30,000-foot view theoretically of what is going on when we do linear regression. And so for those of you that are worried that we were going to do some really serious statistical theory, rest assured we are not. But for those of you that came for that, a little bit of a disappointment that we're not going to get into that, but we want to talk about conceptually what are we doing, when would we want to do it, and then how do we do it in Alteryx. And so the idea with linear regression is that what we're really trying to do is answer a question for us, and that is, as one variable of interest goes up, what does the dependent variable or outcome variable tend to do? So for example, we may think about this in terms of, let's say we're in marketing and we want to know how many people actually click on an ad that we make, and so we may make changes to that ad, and does that make us more clickable or less clickable? But I thought really, since it's still almost 100 degrees here in Texas, I thought what we might do is actually talk about ice cream sales. So let's suppose that we're trying to monitor ice cream sales, and we've got a spot on the concrete out here in Texas, and it's crazy hot, and people are coming by, and so what we want to know is how many ice cream sales can we predict how many ice cream sales we're going to have in a given day at our little ice cream push cart based on the temperature. And so we're going to monitor this from 0 to, let's say, 100 degrees Celsius, and we're looking at, all right, how does the temperature affect ice cream sales? And so we would just call this a bivariate plot, but let's suppose that we plot all this out. So here's our data, and we see, all right, ice cream sales, it looks like they tend to go up as the temperature goes up, and what we can actually do is we can actually fit what's called an ordinary least squares line or a regression line to this data, and maybe it'll look something like that. And so the idea is that can we know for certain, as ice cream sales go up, can we predict about what as the temperature goes up, can we predict about what ice cream sales will be? And so this is really kind of regression in a simple format. It's just taking one variable, trying to predict another, but we're going to actually talk today about, we're going to take multiple variables and try to predict how they interact. Now, let's suppose that we actually have ice cream sales, and let's suppose we're terrible at this, and so we're going to rethink this one, and we don't give a variable that actually correlates well with ice cream sales. And so let's suppose we wanted to look at how does someone's shoe size predict how much ice cream they will buy. All right. So if we were to plot this data, then we might expect that something, that our data set looks something like this. Just shoe sales is just the shoe size is all over the place when compared to ice cream sales. And then if we fit a multiple regression line to this, it might look something like this. So you say, all right, well, Kyle, why the 2 here? So lots of times when we're thinking about linear regression, we're thinking about, okay, how does one variable change in relation to another? Again, that was the whole point of this statement here, is one variable of interest goes up, what does the dependent variable or the outcome variable tend to do? And the reason I have these two plots is it really is all about how good is your variable of interest at predicting the dependent variable or the outcome variable. So in this case, because all these data points are what we say relatively close to the line, they're actually our fitted regression line. They're actually doing a pretty good job of predicting ice cream sales. But in this case, with the shoe size, everyone's pretty disparate around that. And so this case is, it's not, shoe sales is not a very good predictor. Now, it has nothing to do with the inflection of the line or how steep it is or anything like that, or because we're going to see later when we get with the real data that we're going to have some coefficients that are going to be really big, but they really don't mean much to us. And so we need to look at all of these things and go, all right, yes, as this variable changes, it tends to the outcome variable tends to go up or it tends to go down. And again, sometimes up and down is all relative. It doesn't matter if, I mean, it may be going up may be good, going down may be good. It doesn't necessarily matter. But the problem is we don't know how good is that variable at predicting ice cream sales. So again, shoe size looks like it does predict ice cream sales a little bit, but it's just not very good when compared to with the temperature outside. So for that, we're going to look at something called the multiple R squared, and the multiple R squared really drives the bus. What this is going to do, and especially when we get into Alteryx, this is going to tell us how good are our collective variables, how good are they at predicting that dependent variable or that outcome variable. It's going to give us a metric. And so I know some of you are saying, okay, well, how do I know what's a big multiple R squared or R squared? How do I know what's a big one? How do I know what's a small one? And I got the worst answer available for you. It all depends, which is just that answer I'm sure you hate to hear, but it is true. It all depends. So if we are doing cancer research, multiple R squared is a number that goes between 0 and 1. If we're doing cancer research, then a multiple R squared of, let's say, 0.1 or 0.12, that may be huge for us because maybe we're working in an area of cancer research where we just don't know very much at all. So being able to explain 12% variance, well, that's a great thing. Whereas let's suppose we're doing something that, let's say, we know a lot about. Let's say we actually know a whole bunch about ice cream sales, and then we get a multiple R squared of 0.12. In that case, that would be really, really bad. We would hope to have a better R squared of like 0.8 or 0.9, something along those lines. Okay, so it really all depends, and we'll look at some relative values. But again, the multiple R squared drives the bus, and we're going to look at this as soon as we get into Alteryx. Okay. So before we do, a word about data types, because this is going to play a huge factor. And actually, most of the time when I'm working with people and they are asking questions and they go, hey, something's wrong with my analysis, generally it comes back to data types. And so for linear regression, your outcome variable must be continuous, meaning must be integrally or ratio scaled. Or another way to think about this is in Alteryx, it'll be one of these options: int 16, 32, 64, a fixed decimal, floating, a double. Okay, so we're not looking at strings. We're looking at or words or something like that. That would be reserved for maybe we could do it in logistic regression if there's only two options, but that's more of a decision tree type question. So if your outcome variable is continuous, like I don't know, IQ or number of sales that we had, or let's even say a score on a game or something like that, then we're okay to do linear regression. Okay, so that's for the predictor variable, or I mean for the outcome variables. Now for the predictor variables, this is somewhat true too, but we're going to add a couple of things to this. For the predictor variables, they can be a string or they can be dichotomous, meaning they be like a yes or no or true or false or 1 or 0. But if we did put a string in there, and so let's suppose we put in group A, group B, and group C, what will actually happen is Alteryx will do something called dummy coding of these. And so if we have, let's say, 3 options, group A, B, and C, it will actually create 2 variables from those 3 options. And I'm going to show you what this looks like at the end. But suffice it to say, for the most part, we want to keep string variables out of our analysis when we do linear regression. It's going to make things more difficult for us. We'd rather not have to do it, but we can. We just can't do it with the outcome variable. Okay, we can, and I'll show you how in just a second. Okay, so what we're going to do now is and I'm going to leave this up for just a second. I have some data that I put up on my GitHub account, but then we also have it available at this Teknion USA website. And so if you wanted to, you can actually click on the link that Rachel just put in there. And so you should, if you're watching on the webinar, she just put a message to everyone. So if you click down on the chat button, then you should be able to see this. And so that's a link to the Teknion website, or if you're a GitHub person, you can look at the GitHub. All these are free up there. And so we have two data sets, the linear data, the linear to score data set, and then we also have a workflow called dummy coding that's just something that I created that we're going to see there at the end. Okay, so these are the things that we're going to use in our analysis. And now, without further ado, I tell you what we're going to do is we're going to go over to Alteryx, and we're going to start working through this. And so here's the data set, and let's just take a peek at this. And what I'm wanting to know is in this data set, you can see that I have a variable current spend. I have a variable that whether or not they're a rewards member. And so what I did is, this is all simulated data. So it's fake data. It's not actually someone's real data on this. And so, but I just kind of played around with some data. And so what I want to know is, can we predict how much someone is going to spend in our store when they come in? And so are they likely to spend more? Are they likely to spend less? And so this variable right here, this current spend variable, that's the one, man, that's the one that's going to drive the bus for me. That's the one I really, really care about. And so, and if I wanted to look at the distribution of that, I can go ahead and pull that in here, and I'll run this again real quick just so y'all can see, okay, what do these variables look like? And so now, having pulled that out, yeah, that current spend variable, that's oh, let me pull that, there we go. We're seeing quite a bit coming through there, and that's going to give me a lot of information about what my data is actually looking like as it comes through. I care about that the most, that current spend. That's my outcome variable, okay? And here's how we're going to try to predict it. We're going to try to predict it with whether or not they're a rewards member, so 1 or a 0. Also with their current combined income, and so that's divided by 1,000. So you can think of this as, this person here makes 89,000, or family, this one makes 92. The number of credit cards that they have, and then also their age. Now again, too, it's all heuristic data. I was just playing with it just to kind of show you some things, okay? And that's all we're doing with this. All right, so the first thing I might do if I'm doing linear regression is I might do a correlation of all the data. So I'm going to pull in just this Pearson correlation tool, and then having done that, let's look at the output there. We'll see that up there, but we can also see this down in our results browser. And so how we look at this is, we really only care about this first column, because that's the one we're really looking at. We want to see how these 4 variables correlate with current spend. So whether or not they're a rewards member, it's a 0.23, and again, we could square these to get a percentage if we wanted. The combined income 0.43. So looking at roughly about 20% of the correlation between current spend and combined income is about 20%. That's, we would square that value to get that. Number of credit cards, that's a really low correlation, and even lower correlation is the age. Okay, so we might look at this at the first, but really what we care about is getting into running the linear regression. So I'll tell you what, I'm going to go ahead and delete this stuff out just to kind of clean up the desktop just a little bit. All right, and then we are going to pull in our linear regression tool. So now this is in the predictive tab, and then we're going to grab linear regression and pull that down. Okay. So what we're first going to do is we need to define, and this, well, I'll call this one, this says linear regression 29, but I'm going to call it Kyle 1. And then I'm going to select my target variable. That is, again, current spend. That's the outcome variable, dependent variable, however you want to think about it, variable of interest, but that target variable. And then I'm going to put in tell you what, this first time, I'm just going to put in whether or not they are a rewards member. That's all I'm going to let predict my current spend. And I'll go ahead and we'll add all our browses after this. And then let's run this and let's see what we get. So as this is running, again, with most of the predictive tools, what's happening is that, there we go. Okay, what's happening is that the predictive tool is actually spooling up a local version of R, and R is what's driving the tool on this. And again, with most of the tools that are inside here, that's what's going on. Is we're seeing the output that's coming from R. Okay, so so I want to look at the report, and this will give me great information. I'll tell you what, I'll go ahead and put that into a new window so that we can all see it a little bit better. So here's how we would read this analysis. So the intercept, we're just going to leave that alone for right now and not talk about that. But this rewards member variable, that's the variable that we have. The estimate is 11.46. So here's the way to think about this. Remember, we asked the question before, as one variable goes up, what does the other variable tend to do, or the outcome variable tend to do? So in this case, we have current spend is modeled by this rewards member variable. So current spend is the outcome variable, and then rewards member, that's the predictor variable. And this rewards member variable is scored 0 and 1. So 0 meaning they're not a rewards member, and 1 meaning they are. So here's how we interpret this estimate. All right. For people who scored a 1, then they spent $11.46 more than people who scored a 0. So again, for every 1 point change in our independent variable, or the predictor variable, rewards member, how much does current spend change? Now this is kind of an on average, if you will. So, but on average, people who are rewards members spend $11.46 more than people who are not rewards members. And if we come down here to the very end, we can see that this is statistically significant. So because that value there is below 0.05 or whatever threshold we set in there. And again, too, just a word about this statistical significance: you either are or you're not. You're really statistically significant, or you're almost statistical significant. Think of it like a pregnancy test. You're either plus or you're minus. Okay, so in this case, it's below 0.05. That's what we said was our criteria for determining is it statistically significant. So that being a rewards member. So we might come back to our the people that are that run this store and say, hey, get as many people as you can to be rewards members, because it seems like those people spend a lot more money. Okay, however, we make a big caution here. We're doing multiple regression. We're not doing predictive causation. Why do I say that? This is saying that on average, people who are rewards members spend more money. However, someone might only become a rewards member because they already spend more money. So again, this isn't causal. Let's go back to our ice cream sales variable. Ice cream sales in Philadelphia, Pennsylvania, and this is true. Ice cream sales in Philadelphia, Pennsylvania is very much linked to the temperature in Pennsylvania. It's not as much in Texas, but in Pennsylvania it is, right? All right. So someone might say, because that correlation, that if we can cause it to be hotter, then we'll probably see more ice cream sales, which might be true, But here's another correlation. Ice cream sales in Philadelphia is also linked to occurrences of violent crime. And this is interesting, because as violent person-to-person crime goes up, ice cream sales also go up. And what's happening is violent crime is actually a proxy for how hot it is, meaning people are outside more, there's a lot more person-to-person interaction. And so we wouldn't say, hey, if we want ice cream sales to go up, we need to have more violent crime in Pennsylvania, right? That's just ludicrous. And so we need to be careful here that while we're saying is that these things are correlated, we don't saying that they cause each other. We'd have to do a different type of statistics to do that. And so something called path analysis might help, or some other types of analysis, but we're not doing that with multiple regression. We're just saying these things are correlated or they're related to each other. We're not necessarily saying that one of them causes each other. So very, very important. Okay, all right, so having seen this, and remember I said the multiple R squared drives the bus. Okay, Here this is, right here, okay? That multiple R squared. So what that's saying is that this rewards member explains about 5.7% of the variance of current spend. Now, I wouldn't think that's very high, but again, it depends on what you're studying. So for ice cream sales, this is probably pretty bad, but only explaining about 5%. But think of these almost as, if you will, as Venn diagrams. So how much do these two variables overlap or explain each other? And they only overlap about not quite 6%. Okay, that's not a lot, all right? But that's how you tell how good is this predictor. This tells you how much they change relative to each other. This tells you, is it statistically significant, meaning is it better than just random chance? And then, but this value here, the multiple R squared, tells you how good of a predictor is rewards member by itself. Now, when we look at this later, it's going to be like all of our variables together, but we'll talk about that in just a second. So that's what we're looking at so far. Rewards member, as it goes up from 0 to 1, there's $11.46 dollar change. So they spend about $11.50 more. That is statistically significant. And then sometimes we refer to this as practically significant. Okay, practical significance. Okay, so there is the first model. All right, well, I know we don't want to run just one predictor because we have all this other data. We want to include it in our analysis too. So let's go ahead and include everything else. We're going to include combined income, number of credit cards, age. We're going to run all those things. And so again, we're going to spool up Alteryx again. It's going to open up an instance of R, and then R is going to run this analysis for us. And so we can then see, all right, now what's the effect of having all of our variables in this model together? Okay. So again, we're going to go to that output, and I'll make that bigger for you so that we can all talk about this, see it a little bit better. All right. Now, rewards member. Okay, now remember we said that as someone becomes a rewards member, that they would change, or the rewards members tend to spend $11.50 more than non-rewards members. Okay, well that number just went down, right? It's now about $4.69. Okay, why did that go down? Well, because now that we're doing multiple regression, we have multiple variables in our model. Right? So we have these four: rewards member, combined income, number of credit cards, and age. And so what this variable now takes on a new meaning. And what this value here means is how much does our dependent variable change, meaning current spend change, when someone becomes a rewards member in the presence of all of these other variables. Okay. Now there's an inner working relationship between these, and so now we're seeing rewards member doesn't change our dependent variable or our current spend near as much when we see it in the presence of these other variables. And also look at this too. When it was statistically significant that by itself, now we don't see that it's statistically significant anymore. And the reason is that combined income really is doing a lot here. So combined income, it's saying for every 1 point change, meaning for every 1 point move in combined income, and remember we divided by 1,000. So in other words, the way to think about this is for every $1,000 more that someone makes, then we expect them to spend an extra 51 cents in our store. So another way to think about this is if we have two people who everything else is the same, they're a rewards member, they have the same number of credit cards, and they're the same age, then for, let's suppose one of them makes 100,000 and then the other one makes 110,000. The person who makes 110,000, we would expect on average would spend $5.14 more. Again, because it's a $10,000 change, so we multiply that by 10. And these results are statistically significant. Okay. So when we're looking at this, here's kind of the mistake we might make. We might say, all right, well, the combined income, that's really the only variable that's statistically significant, and that's the only one we want to include in our analysis because in these other three are not statistically significant anymore. And so we're going to kick those out and just do combined income. We'll do that in just a second. But remember this number, this multiple R squared, 0.2043. So in other words, these four variables now explain 20% of the dependent variable. That's actually pretty decent for most studies. I mean, that's again, it depends on what we're studying, but that's generally pretty decent. Not too bad, not too terrible. Okay. So when we're looking at that, that's the number we want to remember in our mind. And we may go, all right, I really, now all I care about is combined income. That's all I care about. But again, for the statistician and for the data scientist, really more data is always better. And just because something is not statistically significant over here, it doesn't mean it's not meaningful. Because this column, everything in here is a function of how many people we have in our study. And if we could have a ton more people, we would see that actually some of these variables will become statistically significant, just if we had a ton more people to our study. So again, now we're getting into the weeds of, or wading into the weeds of statistical theory, but this is definitely something I would not want to do, is just to say, all right, I'm going to kick people out because they weren't statistically significant. I mean, if I have 2 million records, yeah, I might. But again, we want to go with caution on this. We can see, though, that age, it seems as people get older, this value would mean as people get older, they tend to spend less, okay? But it's a negligible value, and our p-value is 0.835. So we're probably going to look at that and go, I doubt that age is a good predictor on how much someone is going to spend. Number of credit cards, kind of the same deal, is that they have more credit cards, they tend to spend more, but it's not necessarily a great predictor. Okay, so you're asking yourself the question, all right, Kyle, well, is there an easy way to know how to do this, or which ones are good and which ones aren't? No, there's not. So I'm going to apologize about that. However, if time permits, I'm going to show you a tool that we actually developed at Teknion that will let you know which of these variables is actually really good. Okay, which one's contributing more. All right, so let's keep with this data set, and so let's take it one step further. Okay, we've got all this information coming in here about our own customers, okay? And then we've got this other pool of customers that have never been in our store. They've never been. So I'm going to look at this one, and if you'll see, when I pull this data set up, current spend is not there. There are rewards member, combined income, number of credit cards, and age. Okay, so here's what we want to do. We want to take the results from this data set, and then we want to predict how much do we think people will actually spend who have never been in our store if we can get them in the store. Okay, so if we can get those people in the store, and this might help us for marketing. So for example, let's suppose you had a really great data set on who is likely to buy Netflix or something like that, some online service, okay? And you're trying to figure out, all right, here are the people who have Netflix, and what, and the people who have had Netflix and canceled. And so now who should we target? Well, the targeting the new people, they will not have bought Netflix before, but what we could do is now predict who is likely to buy it or who is likely to spend more on it based on this new data set. So in this one, we're trying to predict, again, we don't have the information on this data set on how much they spend in our store because they've never been there, but we can use the information coming out of this model to predict what these people might have done. And that's really simply done in Alteryx with the score tool. So I'm going to pull the score tool down, and I'm going to connect my data. So this is the new data, and that's going to go into the D anchor. And then out of my linear regression model, I'm going to pull in the information from my model. And then I tell you what, I'll go ahead and add a browse tool after this. So, well, it seems that my Alteryx decided just to stop there for a second. Okay. So I'm going to add this browse tool after. And now when I run this, we will see that, in this case, I'm going to call my new outcome variable. I'll call this new one, let's say predicted spend. Okay. So now if I run this, let's go ahead and run this model. Alteryx is going to take a second, starting to think about things. Okay. Again, we're going to spool up another instance of R. We're going to take the information from this model that we built previously to score this data set for this new people who have not yet been into our store. And then we'll see in the output that what their predicted spend would be. So let's look at this first case. So in this first case, we have this person who is a rewards member. Combined income for their family was $115,000. They have 4 credit cards. This is person is 27 years old, and we're expecting that they are going to spend $98 when they enter our store. So what we could then do if we wanted is actually sort this data by how much they're expected to spend, and then that would give us a good idea of who we wanted to target with our marketing campaign. So we may have information there about who we would want to target. So again, this is the point of when you're in Alteryx and you're building these models with linear regression. After you built a model that you really care about, the whole point is putting that model into production. I think this year at the Inspire conference, they said something like 50% of all models that have been developed are never actually deployed. Deploying is doing this right here, where we are taking new data and then we're using stuff that we know previously and we're scoring that new data based on things that we've learned from our own data in the past. Okay, again, this is really important for marketing. This may be important for, let's say you're predicting how much cash you'll have on hand by some certain factors that are going on within your business. Well, even next week, we're going to talk about how we might possibly want to predict hospital readmission is a really big topic right now in healthcare. And so next week in our logistic regression, we're gonna talk about how do we predict whether or not someone is going to be readmitted to a hospital based on our past data, and then we will actually score future data, meaning people who are currently in the hospital, knowing what's their probability of whether or not they'll be readmitted. Okay, now circling back around to some of the things that I said before, I said I would talk a little bit about dummy coding. Okay. So here is a data set that I just created myself. It's a really simple data set. So I have some Y scores. We got 1, 2, 3, 4, 5, 6, 7, 8, and then 11. And then I've got this variable called name. And let's say the first 3 names are Bob, the second 3 names are Doug, and the third 3 names are Kyle. So in other words, I've got 3 scores coming from Bob, I've got 3 coming from Doug, and then I've got 3 coming from Kyle. And then here's some sort of predictor variable. We'll call it X1. Okay. When I put this into linear regression, okay, I'm going to put in my target variable as Y. I've got name and X1 as my predictor variables. Again, this is also a thing you want to make sure you do. Don't put the variable that's your outcome variable in as a predictor. That's always something just to make sure of. Okay, and then when I run this analysis, I think you'll see something kind of neat because I did that thing that I told you not to do. I put a string in as one of my predictor variables. So let's run Alteryx and then we'll see kind of what happens as our output as a result of this. And I'll show you what dummy coding looks like. So almost done, waiting on Alteryx. There we go. Okay. So let's look at our output. So let me make this bigger so everyone can see. All right, now remember we had 2 variables that we included in our analysis. And the 2 variables were name and X1. So here they are up here. We're modeling this outcome variable Y with name and X1. Well, here's what Alteryx did for us. It automatically dummy coded that variable that we had name. And so remember, there were actually 3 names though. There were Bob, Doug, and Kyle. And what dummy coding does is it says, all right, one of those is our reference point. So Bob is our reference point. And then we're going to create a variable for Doug and we're going to create a variable for Kyle. So here's how we would read this. All right. Anybody who is named Doug in our data set would have a score of 1 on this variable. Of course, they would have a score of 0 on Kyle. And then our reference person is Bob. So how we would look at this, we would say, on the whole, Doug tended to score 2.62 points above Bob. Okay. And then I would also say with this one for Kyle, anyone named Kyle tended to score 4.96 points above Bob, not above Doug, but above Bob. Okay, and then to figure out how much more Kyle scored than Doug, we could just subtract these numbers from each other, and we'd see that Kyle scored about 2.3 points above Doug. Okay, so that's what dummy coding does. I would caution you from doing this, but the reason I wanted to show you this is that, as many of you know, when you have a data set come in with, let's say you import a CSV file, often it imports everything as a string. And so let me show you what can happen. when all of your data come in as a string, I'm going to change this one to a string also. When they all come in as a string, even though we know that x1 isn't a string, we know that it's actually a variable because it's reading any CSV file that comes in as text. As we run this, we'll find out what happens to that variable that should have been a continuous variable or should have been, double or, an INT variable. Let me show you what happens with this. And this is why I just wanted to show you this so you'll be able to recognize it when you actually run this type of analysis. What happened was that variable that was called x1, it dummy coded everything there. So it dummy coded, there's a value called for 3, so it's x1 3, x1 32, x1 5, x1 6, 7, 9. So what it basically did is all of those options that were continuous, it dummy coded all of those so that now we've got an issue, okay, in our analysis. And so when you see something like this, that would be an example of, oh goodness, I must have the wrong format on that variable, and so you need to go back in and change that variable. Okay, all right. Now here's the last thing, and then we're going to open it up to questions. So Rachel's monitoring those, and so as you have questions, please let them put them into the chat, and we'll try to get to as many as we want. All right. So we have built our own at Teknion, our own regression tool, and this tool is called Y-Hat. And the reason we built this is because, well, for 2 reasons. The first is that I had already built a routine or a package inside of R called Y-Hat that does some really cool things with multiple regression, and that's something that we really cared about doing again. So I'm going to add all this to a container and then going to minimize it so that it'll be out of our way. Okay. So that won't run. Oh, come on. There we go. Okay. And then the second reason is that one of the things we noticed is that with the linear regression tool currently inside of Alteryx, you can't tell, when you have a bunch of variables in your analysis, you can't tell the relative contribution of each variable to your model. So what we wanted was a tool that would actually, without having to do all these things one at a time, would actually tell us everything we needed to know completely about our model, so that we didn't have to actually do all this extra work and run a whole bunch of different models against each other. And so again, we optimize a few things. It runs pretty quickly. And also too, the best part is it's freely available on the Teknion website. So all you need to do is navigate there, and I can show you where that is at the end of our session today. But it's freely available to you. We've also done the same thing with the K-means tool. We are looking at doing something with the principal components tool. It's just not quite ready yet for free distribution. But again, we're highly committed to the Alteryx community. And so when we see, all right, hey, here's an opportunity for us to develop a tool, we develop it and then we give it away for free, because it's something I think it makes us all better when we have more tools. And so here is the tool. And what this actually includes in the analysis is a report that will allow you to see the regular unstandardized weights, that's what Alteryx gives you, what's called the beta weights and the structure coefficients, and then also the commonalities. And I'll show you these in this report here, and then why these things are important. Okay, so as we pull this report up, now again, we're getting a little bit of statistical theory, but I think you'll be able to see why we did this. So we told you as before that really what's going on is that the multiple R squared drives the bus, right? Well, what we haven't told you is how do we figure out the multiple R squared and what each variable's contribution is to that multiple R squared. Okay, so what this does is, if you want to think about it, these first 4 rows or 4 columns in addition to the variable, so I guess the first 5 columns, that's the report that you get in Alteryx. So that's what you normally would get out of Alteryx. Now the beta weights I'm not going to talk about those, and I kind of have, the reason is I have feelings about whether or not I think they're good. I think they're only good in one instance for me, and that's when you're discovering something called suppressor effects. But we don't want to talk about that. What we do want to talk about are these structure coefficients. So another way to think about this is that if you'll remember, these four variables are eating 20% of the pie, if you will, of our dependent variable, or the multiple R squared was about 0.20. So they're eating about 20% of that overall pie. What this tells you is the relationship between the part of the pie that you're eating and each of these variables. So the way to look at this, and again, this combined income variable, let's start with that one. This structure coefficient down here is 0.957, okay? That's huge, that's absolutely huge. Which means that these are on a scale from 0 to 1, so that means almost 100% of what we can explain about the dependent variable is done by this combined income by itself. I mean, that's just almost all of it. But if we look down at rewards member, we see rewards member is actually a pretty good variable too, because about half of what we're looking at there is contained inside that. Well, I'm sorry, actually it's about a quarter of what, because we need to square these first. About a quarter, so 0.52 squared is about 25%. So about a quarter of what we see in there is actually explained by this rewards member. So we may look at this study and go, okay, this variable here, combined income, that's statistically significant. These other three aren't, they're terrible predictors. But they're not. Rewards member is actually pretty good, and it's explaining 25%. The problem is that combined income, in the presence of combined income, they kind of explain a little bit of the same thing. And so we would want to look at this output to determine, yeah, maybe one of our things isn't statistically significant, but you know what, there's still, the structure coefficient is still pretty big, which means that really combined income is getting all the credit for it, but rewards member does do some things in helping us understand our model a little bit better. And then we also have down here the commonalities. Again, those of you that are just total stats geeks and stats nerds, you'll care about these, but these are about what part of the variances are unique to each variable and then the commons between them. So I'm not going to take time to explain this part, but I do think this is important, the structure coefficient part, and we get information about where the pie that we're eating, where is it being divvied up, and where does it go. So we thought this was an important tool. Again, when I'm doing model building, this is one of the things I care about a whole lot, because I may put, 10, 12, 15 variables in my initial model, and then I come back and I look at these structure coefficients to go, because I really don't care about p-values. I know it's terrible to say, but I don't. I care more about these structure coefficients. They tell me a lot more than the p-value does, because the p-value is kind of divvied up arbitrarily, if you will, but the structure coefficients are not. These are actual values, and they give me a lot of information about what's going on with my model. So I like this. So again, it is freely available on our Teknion website, and I'll show you that at the end. But I think what we're going to do is stop right now, and then Rachel is going to pull forward some questions, and I'll try to answer just as many as I can in the time that we have left. Okay, so Rachel, go ahead.
Sure. So our first question is, can you remind me again the difference between multiple and adjusted R squared? Is adjusted when variables aren't on the same scale of measurement?
Okay, that's a great question. So so I will say this: the adjusted R squared, there's about 18 of them, and I'm trying to remember off the top of my head. I can't think of exactly which one Alteryx uses, but I think if they're pulling out the one that's just the default inside of R, then it's the query correction. And so what that does is that actually punishes you for using more variables in your model. So it's almost like a parsimony measure. And so the more variables that you use, the more you get punished. And so it gives you more. Basically, if you have 1,000 variables in your model, the multiple R squared and the adjusted R squared are going to be really different from you. But again, there's about 18 different ones, 18 or 19 different ones on these, and they all kind of adjust the R squared based on certain criteria. And again, I think the default is the query or the cloudy maybe, but I think it's the query. And that one basically adjusts for how many variables you have in your model. Okay, great question.
Sure. Next is, what are the 3 outputs of linear regression?
Okay. So if we're looking at the outputs, so this is the first node, that's the model output. So again, I may have to run it again to see that. So this would be this node here, or anchor here. This first one will be, that's the thing that we're going to actually pull in from to score a new model. This R is the report, and then the last one is just giving us information about how it was run. And so again, I'll tell you what, I'll run it again so that we can see all of them. It may take just a second to run, but so why don't we look at the next question, and then we'll come right back to that.
Sure. What's the best way to consider the non-numeric value? How do we use PCA calculation in linear?
Okay, so, oh goodness, I may need more information on the question. So if we are considering a non-numeric value, we really do need to dummy code it ahead of time. What I generally like to do in those types of situations is, if we have a non-numeric value, then I like to make my own dummy code. So for example, let's say we had category A, B, C, and D. Then generally what I will do is I might say, really all I care about is A versus B, C, and D. So I'll create my own variable where I'll just I'll make everyone who has a value of A, I'll give them a 1, and then the people who have B, C, and D, I'll give them a 0, and then I'll include that. So when you have non-numeric data, that's the best way to do that. Again, you've kind of seen how R is going to do that with the dummy coding, or I mean, Alteryx will do that with the dummy coding. But that's really more what I would do, is I would look at those non-numeric values and say, all right, how realistically am I going to use these? And then I would create my own numeric variable based on that. Okay, going back to the previous question though, again, this is actually the output from the model. So you don't see anything in here, but that's where you would push the results from that model forward into scoring. The second anchor, there's the report. That we see coming out, and then this third anchor gives us information about model fit, and so we'll see. Again, let me pull that up. So in this model fit, we'll see again the multiple R squared, the adjusted R squared, and then we have these other variables called the mean absolute error, mean absolute percent error, root mean square error, and then we can actually, if we wanted, we could compute the root mean square error of approximation. These four right here, you would use those, and then the F statistic also. This is like an F1 statistic almost. But you would use those if we're wanting to compare models to each other. So it is possible, and there is actually a pretty cool R tool that's available up on the designer gallery that you can compare different linear regression models, as long as they have the same outcome variable. And so you can look at, and they have to be kind of nested. I know it sounds weird, but it's not like you can use, okay, variables 1, 2, and 3 to explain model A, but then variables 4, 5, and 6 to still explain that, and then compare them. That gets a little bit more difficult to do, and you'd have to do some wrangling there. But on these things, really, you would look for, if you're comparing two models that are nested inside each other, meaning like one of them used predictive variables A, B, and the other one used predictive variables A, B, and C, you would look at these values here and see, all right, how much did they drop with the addition of that new variable, and then how much did how much did they go up? And again, it's a little bit, now you're starting to talk into less theory and more subjective decision making when you do that, but that's that third node. Okay, great question, great question.
Another one is, how do we check the outliers, overfitting and underfitting?
Okay, so the outliers are going to be difficult, and it's funny that you say that, because about 5 days ago, there's another person here at Teknion, and his name is Matthew Agee, and he's been on the Alteryx Grand Prix a couple of times, and they actually now have a new rule where he can't compete again, which is kind of funny to me. But he and I were talking about this very thing, and we actually developed in just 5 days ago. Let me see if I can pull this in. Oops, I didn't want to do that. We are changing the tool. Oh goodness, come on. I'm sorry, I keep clicking on the wrong thing. But we are changing one of our tools. Well, it doesn't appear that. Okay. Regardless, we're changing this Y-hat tool, and it's probably going to come out in about maybe 2 to 3 more weeks. But we're changing our Y-hat tool that now it will give you a graphical interface that will tell you here are the outliers and where they exist, and it will actually be mildly interactive. But it does take some effort to do this, and it will help you identify if you do have outliers in your data set. And so for those of you that are familiar with something called QQ plots, it actually does a mildly interactive QQ plot, and that will help you identify outliers. And so we hope to have that up on our website maybe in 2 to 3 weeks. And so it'll be a newer iteration of the Y-hat tool, probably Y-hat 2.0 or something like that. But that's a great question that we have thought about, and yeah, it is coming very soon. And I'm sorry I don't have that ready to demo for y'all right now. But again, great question, great question.
So I think we only have time for one more. So our last question is, for Y-hat, how do you define your predictive value?
Okay, so if you're in the Y-hat tool, again, up here where it says select dependent variable, that's where you pick that variable. So we would select the current spend, and then that's our dependent variable, and then we select our independent variables down here. So it just automatically defaults to the first variable that appears in your data set, and in this case, that happened to be that current spend variable. Okay. All right, well, great questions, and I really appreciate y'all taking time to meet with us. I know everybody has a really busy day, and so we're honored that you were able to join us. Also, too, please find me on the Teknion website. Again, Kyle Robertson. Always happy to answer questions, or if you have stuff that you're really stumped with, we'd love to. As long as it's something that doesn't require 7 or 8 days to do, we'd love to join you on that. But then also too, we are available for consulting. So if you ever are, hey, we're trying to build our first set of predictive models and we need some maybe someone to help with that, we would love to help you with that. We also build, like I said, this Y-hat tool. We also build custom tools for our customers to do. We recently built one to do A/B testing. Again, I can't show you that one because we built it custom for them, but to do some really special things with A/B testing that then kicks off some Tableau tools and then dashboards in order to do some pretty complicated things. But we love doing that. We'll hope you join us next, and then I'm going to turn it back over to Rachel. All right.
Sure. So just a reminder as we kind of close up is that this webinar was recorded, and the recording will be shared via email within the next few days, definitely before the end of the week. And we hope you guys join us for next week. Kyle will be leading again, covering logistic regression, and then feel free to follow us on all our social medias and then reach out to us whenever you guys have any questions.
Great. I just recalled I promised one thing that I need to do. I'm going to go to the Teknion website, and then I'm going to show you where the free tools that we develop are. So teknionusa.com, and then if we go to products down to Alteryx, then we can scroll down, and we'll see here is our K-means tool that we developed, and then here's the Y-hat tool. So you can download these for free. We would encourage you to use them. Again, the Y-hat tool will be in a 2.0 upgrade probably in the next 3 weeks or so. We are adding that outlier part of that, but we want to. There are a couple more changes that we've seen that that we can actually make it run a little bit faster. And when you get really big data sets, it does tend to bog down a bit. But we're doing some optimization on that also. But you're welcome to use them, and just click on those, and you can be there. All right. Anything else, Rachel?
That's it. Thanks for joining us today.
All right. Thank you all so much.